So yeah, so some clarification uh, of few questions. Right. So number one. So how do we identify so S2 in R3 that you know and CP1, which is a little bit weird, like the definition as you already figured it out. So okay, so I don't think I need to explain what this is, right? So this is just the yeah. But let me just make sure. So as I said, you can write this as a collection of the three tuple satisfying the unit vector condition, and you are able to rewrite it in terms of the spherical coordinate. So I don't think I need to explain anything here. So the like the issue. So for the CP1 is so let's just make sure the definition first. So let me write down two different like the forms. So the CP1 is defined as a point in S3, and we collect the bracket of Z where bracket of Z is the collection. Sorry. So let me write down one more like the line. So C1 comma C2. So it is the two tuple. It's a pair. So this pair at least makes sense. So if you any of you have any like the comments, so just let me know. We regard this sit inside of C2. Is okay with you? Instead of R4. So that Z1 and Z2 are complex numbers such that this is defined as a e to the it z1 with e to the it z2, and t is between 0 and 2 pi. So I first want to make sure each of the description in a clear way. So the step of thinking for CP1, fix, first step, fix any element Z consists of Z1 and Z2 in S3. That's the subset inside of C2. That's your first like the step. Make sure that this is arbitrary element. So let me make sure that this is any element. We consider any element in S3. So this condition, S3 means that Z1, Z1 bar plus Z2, Z2 bar equal 1. Is that okay with you up to here? So you first choose Z arbitrarily from S3, and then you make the bracket of Z. Bracket of Z itself is the set, and in the problem set 3, of course, we'd like to clarify the term, each terms, but this is usually called by the equivalent class. In the term of the problem set 3, equivalent class of Z, which is defined as I already wrote, but let me just rewrite it again. Because Z1, Z2 are already fixed, so that this makes sense to consider each of the pair depending on T, and we consider the range of the T from 0 to pi, but can be any vector here. But so this is a description. And then you collect all of these like the equivalent class of Z, and Z varies arbitrarily on S3. So this is the definition of the CP1. That's the way of thinking in the procedure. Is that okay with you? You have a Z in S3, and then you make the equivalent class, and then as a we just regard it as an element and collect all of them, then that collection becomes CP1. That's the definition first. So if you guys have any questions, let me know. So so as you know, on the other hand, is that okay with you up to here, by the way? So for the weird description of the CP1, of course, this is not the form you saw from the problem set, but I'm saying that these are all just a coincide. So this is the one like the description you should know. That's what I'm saying. Is that okay with you up to here? This three step of the like the explanation of the CP1. If you like the explain the definition of CP1 to the audience. So I recommend you to follow this step instead of just giving, yeah, well, but like the equivalent relation and so on and so on. Don't do that. Just to say, let's start from the S3 in C2 and collect. So consider all of the that's a element in S3 or the unit vector in C2 from the complex Hilbert space C2. Is that okay with you? And then we consider all like the bracket of Z, it corresponds to the gray circle in the Hopf vibration. Is that okay with you? And then we collect all those like the gray circle, then that becomes the definition of the CP1. That's but on the other hand, as you feel really like the weird, so you already saw the definition of CP1 was the following. So it is the collection of the Z1 versus Z2 with the bracket notation. Is that okay with you? This notation. And then you have Z1 and Z2 in C2. This is also another description of the same definition. Let me know if you have any like comments or questions.
Sorry, what does the notation with the brackets mean exactly? Is that like an equivalence class
It's
or
the same equivalence class, but let me clarify for that. So you're asking this,
yes.
right? So this is defined as a collection of the also the pair lambda z1 comma lambda z2. Here lambda is any like the non-zero complex number. So and this is the just it describes the set of the collection consists of lambda z1 with lambda z2 where lambda is any non-zero complex number. So for example, can you see these two are the same? Because we can multiply arbitrarily lambda so that if you start from say here, you start from the pair of the z1 comma z2, and then you will multiply arbitrarily lambda, non-zero complex lambda. Is that okay with you? And in this case, you start from 2z1 with 2z2, then if you multiply by any lambda, it's just the same as a set. And for example, if you don't get it, let me know. If you multiply by, say, negative 100 z1 versus negative 100 z2, because we will multiply arbitrarily non-zero complex value so that as a collection, they are the same. That's what I'm saying. Does that make sense to you? So let me just give you one more such a like the example. This is also the same. However, I wanna make sure that you to follow this like the rule completely. So for example, this is not the same because we should multiply the lambda on each component of the pair. So there's no way to go from one to the other from here to here by multiplying some of the lambda non-zero complex like the value. Does that make sense to you? So this is like the necessity that so you need to understand why they're the same, why this is not the same. Let me know if you have a like a difficulty to understand, like to convince yourself that this is not the case. Let me just make sure. CP1 can be also regarded collection of this bracket of the Z1 versus Z2, and this like the Z1 versus Z2 itself is a set defined in this way. And this like the collection is that's given by multiplying any non-zero complex value lambda on the on component at the same time. So because of that, so if you start from z1 comma negative z2, there's no way to recover z1 comma z2. But you can recover 2z1 with 2z2. You can recover negative 100 z1 with negative 100 z2, but not this guy. Is that okay with you up to here? So now also you need to really like the click why those two descriptions are exactly the same. But yeah, so I at least give you two distinct like the description of the CP1. One is like this like the weird one, e to the itz1 with e to the itz2. That's the bracket of z, and then we collect them. And this is slightly it looks a little bit different. So let's just try to recover from one to the other. So for example, let's just play with it. So if you have this guy, This is same as this guy. So all we are using is just this definition. Again, this notation represents a set. We will multiply any non-zero complex like the value. So are you really convince yourself that this is the case? Is okay with you? Because we will multiply by any like the non-zero like the complex like the value. So let me just write down one more time. So this is the collection of the, let me say, what is a good like the notation? So let me say mu z1 comma mu z2. Here mu is any like the complex like the value. That's the meaning of this notation. So this notation means collection of the mu lambda z1 comma mu lambda z2. Also mu is any non-zero complex value. Can you convince yourself that those two must be the same? Because we will multiply all possible those like the mu values. So as a set, they must be the same. Are you really with me? Let's just make one more example before we go further. So for example, let's just choose z1 comma z2 as say 1 comma 2, 1 comma 2. Then this guy means the bracket of 1 versus 2. Then this means, so I'm just again using just this definition. So this means collection of the lambda times 1 with lambda times 2, where lambda is any non-zero complex like a value. I just apply the definition. Are you with me? So that this means this is same as the collection of the pair consists of lambda with 2 lambda with the same condition. Are you with me up to here? Then this means, so please like to follow this like the part by yourself. Otherwise, let me know. It's fine. It's completely fine. So for example, so we multiply by 2. So eventually this is same as 2 versus 4, 3 versus 6, 4 versus 8, and so on. However, this is not same as 1 versus negative 2. That's not possible. Are you with me up to here?
Wait, this makes sense. I'm just wondering, is there like a visual intuition for this? Like what we're
I will
doing?
give it a visual
Okay.
like interpretation. This you already
Okay.
have the visual interpretation, but you just need to click with your like the match with your intuition. So now, so yeah, anyhow, I now assume you understand this like the example. So like logically, how this makes sense. So from the like the definition, then now just let's relook at this guy. Relook at this guy. Then please just follow this like the following way. So this is the same representative eventually for any non-zero complex value lambda. Are you with me up to here? So those two are the same. That's what we said from the concrete example. Are you with me up to here? So if you okay with up to here, so we can choose this complex value as a e to the it. You agree? Because we said this is true for any lambda as long as lambda is non-zero complex value. Are you with me? So let's just choose lambda to be e to the it. What is e to the it? E to the it represent the element of on the unit circle. Are you with me? T, this is e to the it. Is it okay with you? So in C1, by the way. So e to the it represent the element on the unit circle in the complex plane. Are you with me up to here? So let's just plug in lambda value to be e to the it. So then you will get e to the it z1 versus e to the it z2. Are you with me up to here? Because this was true for any lambda. So why don't we choose lambda to be e to the it? That's also okay. Logically, that's fine. So now let's just go back to the definition over here. Definition over here. So you see, we are multiplying by the same weight of the lambda. Just in this case, it's just a given by just a e to the it at the same time for t from 0 to 2 pi. So it's kind of the scaling effect. So now let me just explain the definition of the problem set. So this guy, so if you look at the definition of the problem set, we start from C2 minus 0, and we identify Z with lambda Z. Here, lambda is non-zero complex lactal value. This is actually the real definition of the CP1. But if you just make the scaling on lambda, then we just collect the unit vectors because it makes sense. So before I go further, what I'm saying is that, so because we will just make the identification between Z and lambda Z, what I'm saying here is that Z consists of Z1 and Z2, right? Lambda Z means lambda Z1 with lambda Z2. As long as we can go from one to the other by multiplying lambda, then we will identify them as the same. So this is a key part of the understanding. Is that okay with you? So let me just repeat. This like the messy notation just mean that we are collecting or like the Z or Z, which is that is the pair. And as long as one can go from one to the other by multiplying by lambda, then we just regard them as the same element. Is that okay with you? But the second line means, so we'd like to make the scaling on lambda, so that why don't we just collect the unit vectors? Is that possible? Yes, it's possible. Because we can always multiply by non-zero, like the complex like the value. So by just making this something like some like the corresponding scaling, we can always make this to be happen. Does that make sense to you? By multiplying some lambda value, but still, but still, it's also still possible that there's another like the t that makes this to be happen. So that still we should identify z with e to the it z. B to the e to the it, the magnitude is just still 1. So those two are all unit vectors. Are you with me? Those two are all unit vectors as well. So, but the perspective is slightly different. So first perspective here is that we consider arbitrarily like the vector in C2, but we identify this way. But we know that we can make the scaling on lambda so that we start from just collecting the unit vectors. Then we still need to identify these two. Still, these two is the same relation from here. Because as long as z is identified lambda times z, z should identify e to the itz. Why not? And because we are only collecting the unit vectors. The previous perspective, collecting any vector, so we multiply by lambda. The later case, we collecting the unit vectors, so that we should identify z with e to the itz. Of course, t is between 0 and 2 pi. Then now this becomes, as you see, so unit vectors in C2 means what? S3. Identification of this guy means the gray circle. S1. This is the Hopf fibration. So now let me just go back. So this answer your like the first question. So the first perspective here, this means we identify S3 by S1. So that this just means that we have the unit vectors in C2. And then we identify Z with e to the itz. This now becomes this guy from the problem set 3. This is the perspective here. So this is the perspective of the Hopf fibration. And the second perspective here is that we just start from the arbitrary vector in C2 and then multiply by any non-zero, like the complex value. But actually, those means the same as you are already. I hope you convince yourself that they are actually the same. But yeah, so this didn't answer like the question why this is same as S2. But I first like to explain what is CP1. So up to here, so before we try to see why S2 is same as a CP1, so let me know if you have any like questions up to here. So yeah, I know this is very like the abstract. So please do not like the disappoint on yourself that if you really do not like the click yet, this takes a lot of time, even for the math like the major graduate like the students. So it takes time. So it's completely fine. If you try to be honest yourself, if you don't get it yet, it's fine. It's very normal. It's fine. Even for a very like clever like the students. Up to you. Is that okay with you? So is this okay? Is this okay? Then so let's just go back. Why CP1 is same as S2? So well, this actually requires a lot of like the different like the perspective. Uh let me try to like be rigorous first. And so let me just give you the two different like the answers. So rigorous answer first. So this could be helpful. And another part is an intuitive answer. So let me proceed to. So now you know we have S3 in C2, right? And then what I will do is, so I will just define the map. So if you choose arbitrary element Z, this Z consists of Z1 and Z2. Are you with me? So this Z1 and Z2 satisfying Z1, Z1 bar plus Z2, Z2 bar equal 1. I'd like to define the map. Then what is the natural like the assignment here? Let's just use bracket of Z1 versus Z2. This means that this is a collection of the pair lambda Z1, comma lambda Z2. But let me just make sure that what I'm saying is that I just need to collect e to the it Z1 with e to the it Z2, where this t is from 0 to 2 pi. So this just means that the codomain of this map is S1 quotient out by this S3 quotient out by S1. So that I have just a map from S3 to the S3 quotient out by S1. So because this is the element of this like the set. If you don't get it, let me know. So what I'm saying is from the problem set 3, so that's the whole point of like the practicing this kind of the very like the hard one. I know it. This is very hard for the undergraduate and for the first place. Let me try to make sure that you really get it. So I will go back to coming back to my like the iPad like the screen, but let's just go back to the project set 3. You know this for sure. So from here, you know the description of this guy. So this like the quotient set is the collection of the equivalent like the class, this bracket of like the A here. Is that okay with you? And then, so hopefully now this kind of makes sense. So this is today we are, yeah, looking at together. So this is a one perspective. Is that okay with you up to here? Because we identify those two in this way. But if you just take this to the unit vector, then this lambda just becomes e to the it because we are only looking at the unit vectors. So at least I try to match with the notation from the problem set 3 so that you can just compare from with my note. So let me now just go back. Okay. So so in this case, so what you can see is so it's kind of hard to but yeah, before we identify with S2, so let me know up to here, is that make sense to you? Or so before we identify with it, just S2, I'm just talking about this map pi. Is that whether or not this makes sense to you? Uh, so before talking about the like there's the rest of the rigorous like the part. So this is the way of like the thinking, way of the thinking. So if you have this guy, right? I will play two things. So if Z1 is non-zero, then I will, so let me just make lambda Z1 with lambda Z2. Is that okay with you? But let me just choose for lambda given by 1 over Z1. Is this okay? Because as Z1 is non-zero, 1 over Z1 is well defined as a complex vector value. So then you can plug in lambda equals 1 over Z1. Is that okay with you? Let's do it. then you can see what's the first like the component? What is the first component?
One.
What's the second component?
Z2 over Z1.
Is that okay with you? If Z1 is non-zero, is that okay with you? On the other hand, let me just choose the same element. If Z2 is non-zero, then let me also choose lambda to be 1 over Z2. 1 over Z2, okay? Then what happened? What's the first component?
Z1 over Z2.
B1 over Z2. What about next?
1.
1. Is that okay with you? So it is important to realize if you compare these two, what happened? They are inverse to each other. So let's just take just write, say Z as Z1 over Z2. Then you can see that this is same as 1 versus Z. This guy means 1 over Z versus 1. Are you with me? So, and from the definition of the CP1, make sure that we will not make the zero vector. So we always neglect the zero vector, by the way. Zero is not allowed. Is that okay with you? So that at least Z1 or Z2, any of them, but so we are not allowed to make both of them equal zero. Is that okay with you? So either case should be satisfied. Either Z1 is non-zero or Z2 is non-zero. At least either of them should be correct. Or of course, it's just a bit true for both of them, but at least this is correct. Then now you need to play the following game. So the intuitive like the answer is the following. So start from C1. C1 means what? Plane. Are you with me? You have a plane. Then let's just choose Z. Z means Z2 over Z1. So even I wrote this as a Z, but the reality is what? This is same as 1 versus Z. Because 1 is fixed, I don't need to care. But Z could be regarded as a Z2 over Z1. Are you with me? Is that okay with you? Then you agree with this because Z equals Z2 over Z1. So I just replace it. Is that okay with you up to here? Then this equals this guy. That's what we said up to here. What does that mean? So now let me draw the two-dimensional sphere. So what I'm saying, so I want you to imagine by yourself. So what I'm doing is that I will just put the point from the infinity. So this is a little bit hard to imagine, but if you have a infinity as a one point, then just attach the infinity from the plane. You have a plane. There's another point outside that we will call it by the infinity point. Just attach. Can you see? This becomes the two-dimensional sphere. Then you get,
So is the plane like plane is like
yep. It's
like
like the element of the plane correspond to the element of the two-dimensional sphere, except for the North Pole. You start from the plane, and each point can be represented by Z, and then you just attach the point of the infinity. Then what is this point? This point is 1 over Z. So there's no such a point on the plane. And this is still represented by Z1 versus Z2 because you know they are inverse to each other, right? One is Z with respect to the origin here on the plane. And if we just consider the infinity point, then becomes just we flip the Z by 1 over Z. Then if you add this 1 over z, it becomes two-dimensional sphere. I think this is most like an intuitive version of the explanation. So why you start from here? You start from z, but z really actually means this guy. Now it's a little bit fancy. This really means actually this guy. This actually can be also regarded as this guy. Then this, what is 1 over z? 1 over z is something outside that we will call it by the point of the infinity. And if you also like to consider this point, then so not only just the or point of the plane, you need to add one more point. That's the North Pole, so that we get this guy. That's a good intuition, so that you can think about it. This is mathematically completely like correct, like the intuition, but you need to try to digest by yourself. And let's just try to see from the equation. So why this is indeed the case. So let me just try to give you the answer. I know this is a little bit heavy, I know it, but still. So then you want to see claim phi of z is in S2. This is what you would like to check. Does that make sense to you? Because we know this guy is CP1 by this is the definition. And if I go back to Angela's original question, why CP1 becomes S2, right? That means that I just need now to see that why each point is in S2, because these are just element of the CP1, why they are the same. So you can really try to write this out. So this means that this is same as a z of pi of z1 comma z2. So one can write this guy as an element of, so let me write this as a x1, comma x2, comma x3 in R3. I should write in this way. So this x1, x2, x3 are the following. Let me give it the explicit just a form. So 2 times real of like the z1 bar z2. X2 is 2 times imaginary number of z1 bar z2. X3 is z1 norm square minus z2 norm square. And you can check that x1 square plus x2 square plus x3 square equal 1. So this is just a mathematically correct like the answer in a sense that you can really check that CP1 element just satisfy the equation of the just a sphere. This can be just justified. Just that's it. But this does not give you the good intuition in my opinion. So this is the way to like the justify. But yeah, so you can take a look and if you don't get it, you can just keep asking later on. But what I want you to like the thing is the following way. So let me just stop the record for a moment. So this is the way of the thinking. Start from the three-dimensional sphere. Three-dimensional sphere. This is the way of explanation to the others. Then you consider each point. Then we have a bracket of z. Bracket of z just correspond to the gray circle. It's okay with you? Gray circle, and we collect the gray circles that correspond to S3 quotient out by S1. Then from either the intuitive justification or the rigorous justification, you can just see that S1 quotient out by S3 quotient out by S1, which is the definition of CP1, that correspond to just S2. And it follows from the Hopf fibration. You can simply just say so. So this is sort of the magic curve, like the justification that S3 quotient out by S1, which is CP1, is just becomes just a S2. So the collection of the gray circles just becomes just S2. So that's my first like the justification. So that answers first like the question. Let me now just I know this is heavy, but yeah, trust me. So as long as you are following this in this like the early stage of the like the college life, could be very beneficial for you. So this is like a very heavy level of the abstraction in mathematics. So I know this could be very heavy.
Sorry, could you repeat? Wait, how does the Hopf vibration, uh, like, how is that related to this? Or
Absolutely. So let me reshare the Wikipedia page of the Hopf vibration. This is also part of your another question. I know it. So yeah, so we look at this like the photo, right? We look at this photo. So we view this like the entire like the set not as a S2 but as 3. Is that okay with you? S3. So you start from here. You start from it. And this notation is part of your question, by the way, right? Part of your like the question. So even it says it maps to S2, but you should regard this as CP1. So you should replace this notation as a S3 quotient out by S1. Is that okay with you? Then what we are saying is that if you don't understand it, let me know for any of you. So you start from Z from here. You start from Z. Is that okay with you? This maps to bracket of Z. What is the bracket of Z? So e to the itz, or all of them together. Let me explain again. You start from here. So it's the collection of Z, and we will map this to be bracket of Z. Is it okay with you? What is the bracket of Z? Collection of this, right? E to the itz1 with e to the itz2. Now you really need to match with your intuition. This is very important, like a part of the understanding. What is the meaning of this guy? We just change the angle for each component. Are you with me? E to the it multiplying by e to the it means we just rotate for each of the components. But we will like the change the t value from 0 to 2 pi. What does that mean? We will rotate completely, one cycle. So this is your time to really imagine. If you have a z1, if you multiply by e to the it on z1, and you will change the t value from 0 to pi, you should go back. But you need to rotate one circle. You repeat for z2 altogether. So that means now you should really imagine how it actually really look like. You have a three-dimensional sphere, S3. You choose any point. Then what is the meaning of the bracket of z? You rotate it along the circle. Then you will come back to the original point. That's the meaning of the bracket of z. Is that okay with you? As a set, is that really make sense to you? This is the most important, like the intuition. So let me just repeat again, as this is important. Start from S3, choose arbitrary point on S3, and consider bracket of z. That means that you just rotate along the circle, and you should go back. That's the photo of the Hopf fibration. Can you just match with the photo of the Hopf fibration for each like the cycles? So that you should regard each of those like the circle correspond to one of the bracket of z. So one bracket of z1, bracket of z2, bracket of z3, and so on and so on. And this guy is in fact S3 quotient out by S1 in my note, like this. So as in my note, so we map from S3 to S3 quotient out by S1. This is CP1, CP1. So we consider the collection of those like the circles on S3. Is okay with you? Then Hopf fibration says it becomes S2. That's the Bloch sphere. So I know this is highly, and this is the justification. I mean, this part is complete justification why this is the case. So the intuitive, like the answer is the answer from the definition of the CP1, and this is indeed coming from this map of the Hopf fibration. So this part is coming from. I know this is heavy, so it's even okay. Then you don't completely like, get it, but you can keep asking. It's completely fine. Hopf fibration, just by definition of CP1. But either cases, they are the same. And the Wikipedia page already identifies CP1 as S2. So that's why the Wikipedia page just write from S3 to S2 directly. But the reality is S2 correspond to S3 quotient by S1, CP1. Does that make sense to you? Yeah, before moving forward, let me know if you don't get it. So let me just summarize up to this like a lengthy conversation. So you can just cite this as a fact. That's completely fine. that CP1 can be mathematically identified, or you can say geometrically same as just S2. And there are a bunch of ways to identify, but one way to take the intuition for our like the project is that we follow the Hopf vibration, start from S3 in C2, then each Z, we consider the bracket of Z. Bracket of Z just means the one cycle containing that Z, and we consider the collection of those like the bracket of Z that give us the map from S3 to S3. Let me just simply now say from now on, S3 to CP1. Is okay with you? CP1, its definition is S3 quotient by S1. Is okay with you? S3 to CP1, then we know that CP1 is just S2. So Hopf vibration give us the map from S3 to S2. And this S2 is the definition of the Bloch sphere. Is that okay with you? So before I ask you like the question, so let me also justify one more like the question directly. So another question, question three. So what is the meaning of this weird notation? This guy. So this notation means the following. So meaning of notations. So let's just split into several pieces. So what is this guy? This guy is nothing but the Hopf vibration. Is it okay with you? This means just Hopf vibration. Let me just repeat. This just means Z consists of Z1, comma Z2. We just map this to be bracket of Z. Consists of like the say e to the lambda t Z1 with e to the lambda it Z2. And this part justify why this becomes sphere, two-dimensional sphere. Is it okay with you? This is the way to justify. You can take a look. So what is the meaning of this guy? So this means this is a, let me just write down correctly, as a fiber of Hopf vibration map, Hopf vibration map pi. What does that mean? This means very easy. So do not like to get overwhelming. It's fine. So this means IE. So it means for each, this is the part of my question. You need to give me the answer back right now. So for each element, P in S2, which is CP1. Okay, so let's just take the point from here first. And fiber means this guy. Let me give you the definition. What does this mean? So this means consider Z in S3 such that pi of Z equals P. This is the definition of the fiber. So you can just think of this as you have a three-dimensional sphere, and now you have a two-dimensional sphere. I cannot really visualize S3. So you have a map pi, then you choose the point P from here, and you are looking at all possible like the Z that maps to P. But what is this guy? This is equivalent class of Z, bracket of Z. What is this guy? Do you agree? So because we already said S2 is the collection of the circles, so the point of P actually is nothing but the bracket of Z. So bracket of Z just correspond to all like the possible like the point of e to the itz1 with e to the itz2, right? For each of the point. So what is this guy? This guy is S1. So that's the meaning of this guy. So you should imagine like this. So you start from the Hopf vibration map S3 to S2. Then you choose any point on S2. What is that point? Bracket of Z. Then you are looking all possible like the element that maps to bracket of Z. What are them? This guy. Does that make sense to you? And this matched as S1. So it's a sort of the subset. So that's why in the Wikipedia page, so that's why it's used some a little bit like the different like the arrow. This means it's kind of a subset inside of the S3. what's the mean? So what's the meaning of it? So it's like the circle is in on the like the three-dimensional sphere. That's the meaning of the notation. This answer like the question of the third one. So I think I justify first one and the third one. Let me know if you don't get it regarding those two questions. So the answer here is as a fiber. Fiber means, let me just repeat. Fiber means this guy. This is a definition, but it can be identified just as one. So that we just regard, because it is clear that fiber is the subset inside of S3, but we just simply just wrote as just S1. It means the following. Whatever point you choose, so this notation mean,
Sorry, you're sharing the Wikipedia page right now.
sorry.
No,
I'm
you're good.
sorry. Yeah. I'm a little bit excited. Sorry for that. So what I'm saying is the fiber means, so it is defined for, in terms of this like the set, this is the definition, but this can be identified as S1. This means the following. So S1 sit inside S3 means whatever for any point, for any P in S2, the fiber, each fiber, pi inverse of P is same as S1. So that's why we just, instead of denote pi inverse of P is inside of S3, we just change the notation as S1 sit inside of S3. That's the notation. It just means, so we have a three-dimensional sphere, we have a fiber, and we identify this as S1 for each of the fiber. It's correspond to the Hopf fibration exactly for each of the, just like the cycles. Okay. So let's also clarify the terms from the question two. Let me now go back to the project set three. So there are several like the terms. So first, so this is a just general definition in like the set theory regarding the term of the quotient set. Is that okay with you? Quotient set, and we apply this definition to just a CP1. That's what we are trying to do. Is that okay with you? So that we have a just general definition of the quotient set. Is that okay with you? So, and in order to consider this like the tilde notation, so this tilde notation is defined in terms of the equivalence relation. So that what you check from the problem set three is that, so the relation we define in this way indeed satisfies the equivalence relation. Is it okay with you? That's the part of the like the problem set. So that, and now you can convince yourself that this is exactly what we today just described. Is it okay with you? So that this is a quotient set. So you can say, so CP1 can be defined as a quotient set of the equivalent relation given by this guy. That's the first term clarification. Is that okay with you? First term clarification. And in order to do it, we use the concept of the group action and the orbit. And this is the part of the definition of the group action here. Is it okay with you? Then let me ask you. So we are using this. We are using this. What is X? So for CP1, I'm asking for CP1. What is X and what is G? So we are exactly using these two like the like the sections, so that in order to describe it, so we should require the concept of the group, and we also have a set. So let me give you the like the list of the potential candidates. So from the Hopf fibers, what do you have? You start from S3, then you map to where? S3 quotient by S1. Is that okay with you? Then what could be the answer? What should be the G and what should be X? Let me give you this. So this is not new. So you already know it. You just need to get familiar with this, that the new terms. So
First,
this
may I
X, yep.
is one of them the Great Circle? Like, um,
So X is S3, G is S1. Now let me try to explain. So what is S1? Collection of e to the it, right? I'm saying this becomes a group. We saw this before, but at this point, let's just make sure. So meaning of the group just means close under the multiplication. Is that clear with you? Close under the multiplication, meaning that e to the it1 times e to the it2 is what? From the exponential law, you should get this. And you have the identity element. What is identity element? 1. 1 is just nothing but e to the I times 0. You also have the inverse element. For each e to the it, what is it?
To the e to the I negative 2.
Exactly, e to the negative it, so that you get 1. So as long as it satisfies, of course, so yeah, as long as it satisfies this to like the three rules, that we call such a set a group. Is that okay with you? So in our context, we use this G for by just S1. Is that okay with you? So now let me try to match with the notation of the like that section. So we use the notation. Let me just use the same notation as the problem said. You can just compare. So you have S1. This is G, and it acts on S3. So in order to describe it, you should get the action. I'm assuming you are looking the problems at three together. Okay. So in order to describe this guy, you should get the concept of the action. What is the action? So you have a e to the it, you have a z, consists of z1 and z2, as you know. You already saw this actually several times with me. Z1, Z1 bar plus Z2, Z2 bar, but you just need to click. This is a fancy concept. So then how do we define this like the group action? What was the definition? This is not new. Again, you already know it. So you choose e to the it from S1, you choose z from S3. What should be the definition of the group action?
E to the IT Z1 and then E to the IT
Yeah,
Z2.
this is not new at all. So with this in your mind, let's just look at the problem set three together. Now you know the concrete definition of this guy in our context. So now let me ask you this. What is the meaning of this guy in our context? What is the identity?
When you multiply or when you do like E to the I0
Just
and
the
apply
one,
it to
right? E to the
Z0,
I0.
Z1, it's the
It
same
will
thing.
not change anything. Are you with me? So if you have 1 dot z, it is z. That's the first condition. Is that okay with you? Give me the answer of this condition. What does this mean?
Like associativity.
Yep. So you have a e to the it1, you have a e to the it2, and if you act on this like the z, then you get this. Just that's it. Is that very clear with you? E to the it2z, and then you multiply by further e to the it1, then you can first just consider e to the I of t1 plus t2 and act on this like the z. That must be the same. So that it match this or requirement of the group action. Is that okay with you? And by the way, this is exactly just the same from the Hopf vibration, by the way, right? So this is not new, just a new perspective. Now let's look at this. So now you have this. Now you have this. Now it's your turn. What is this? So now let me make sure. Given a group action, so again, X correspond to S3, G correspond to S1. Do you agree? And now you know the concrete expression of this guy. Is that okay with you up to here? You choose one element. What is this? You choose any element from S3, right? So you pick up Z. You choose Z here. Is it okay with you? Z. So please give me the description of what this is. What is it?
Is this like all the places it can do after applying? the
It's
group action.
valid intuition, I agree. So let's just try to get further. So
They're
what is,
just like a circle.
let me write it. So also, O sub x, but let me try to be a little bit more fancy because now we are learning mathematics. O sub x, but this is the correct notation. So it says g dot x, and this g is taken from this capital G. So now let me just change the notation. So let's just replace x by z. So this z consists of z1 and z2 in our context, right? So this means e to the it dot z, you agree? And this e to the it is taken from S1. I just copy. Do you agree? Then this means this is same as what? E to the it z1, comma e to the it z2. And this condition, the requirement just means t is from 0 to 2 pi. What is it? This is exactly the bracket of z. Do you agree? And in the context of the group action, this is called by the orbit. So orbit just means nothing but the gray circle. Do you match? So you start from the S3. This corresponds to the orbit, but I just say just in general, just a group, just a gray circle. This I think this addresses more intuition, but it's just the same thing. So now let's just go back to the problem set 3 again. Hopefully now you already all know the answer. Orbit space means the collection of the orbit. Is okay with you? What is the orbit? Orbit is the gray circle. So that this is the collection of the gray circle. That's the orbit space. Are you with me? Now you understand my question. What is it? You start from S3, and we have a bracket of Z. That's the gray circles. And if we collect the gray circles,
S3 quotient S1, so
yeah,
S2.
yeah, that's the answer. So the rigorous answer, S3 quotient by S1, this is what? CP1, which is exactly same as S2. So, and this is we call it by the Bloch sphere. I think this completely like clarify all the term clarification. So that you can use whatever term you prefer, but if you can say the following. So if we that's a reinterpret from the context of the group action, then the great so what we consider bracket of Z can be regarded as the orbit in S3, and the orbit space turns out to be S3 quotient by S1. This is a definition of the CP1. And it turns out that this is same as S2. That's we call it by the Hopf, just call it by the Bloch sphere. At this point, I want to just add one more like the term so that you should know. So because you are now doing quantum computing project, what's the definition of the collection of the one qubit? Bloch sphere. That's the definition. Let me just repeat. Bloch sphere is the collection of the one qubits. Mathematical reality is what? Collection of the gray circles. Are you with me? Gray circles. We regard one qubit not as just an element of the C2. The one cycle, I mean gray circle, correspond to one qubit, meaning that we don't care the effect of the multiplying by e to the it. We regard all those them as just the same single element. That's the concept of one qubit. So let me just repeat. One qubit that we replace from the bit in the classical computer is not just the element of C2, it is the element of the all possible e to the it z1 with e to the it z2. So it's the orbit itself is the one qubit. That's what you have like to put a lot of effort is like the June and July to really catch up the mathematical like the prerequisite of the quantum computing. Is that okay with you? Let me just repeat. One qubit corresponds to what? Orbit. And in order to describe it, you can use either the group like the group action that you put the effort to understand it, or so gray circle from the Hopf vibration, whatever they are the same. So this answers first like the three like the questions, and now you see the difference here, right? So that we just change the perspective. Let me just make sure. So just the difference? So I just want you to equip with the perspective so that this can be used for your presentation as well. So usual Hopf fibration means this guy, meaning that if you start from Z, consists of Z1 and Z2, then it maps to where? So e to the it Z1, comma e to the it Z2, where t is between 0 and 2 pi. Then this is Hopf fibration that we have discussed today. Is it okay with you? The weighted version. So this is now new. So weighted version. So we introduce positive so we just choose any positive integers a and b. Then we change the map. We change the map depending on this a and b from S3 to this guy. Still the same, but if you have this guy, then what you know is this one is now changed in the following way. So now it is very like the different situation compared to the previous case. So I just want to match the just one single intuition for you. So, but mathematically, I think this like the description makes sense to you logically. Is it okay with you up to here? Logically makes sense. Intuition, we need to work. So intuition. So if A and B are equal one, it's just tedious, right? Then just a previous case. So just a previous case. So what we are doing covers the previous, like the understanding of the one qubit. That's fine. So if you take, for example, A equals 2, B equal 1, what happened? So if you change, so say T from 0 to 2 pi, so from 0 to 2 pi, anyhow, it should rotate one circle. Is that okay with you? Still, that is okay. However, for the first component, it actually rotate twice. First component should rotate twice. Are you with me? Whereas second component rotate just one time. So it's now like a more like the twisted a lot. It's really hard to really visualize at this point. There's no like a good visualization, by the way.
When it rotates twice, it's not like the same rotation.
It's not the same
Like
rotation in a sense
it's
that the previous case that Z is the pair, Z1 with Z2. So they rotate all together one time so that it just go back to the original point from 0 to 2 pi. But it's not like that. So Z1 is already rotating twice, whereas Z2 just rotate one time. So it's kind of I do not know how to even draw it. So you two might have a better like the intuition than I do. So it's kind of the rotate one time again. I do not know how to even draw it. So it just draw in the like the rotate in the a very like crazy way. But anyhow, it also draw one circle, but in a very like the weird way. And we still collect all those. That's the definition of the weighted projective line. So now you can just look at the manuscript why one need to consider. This is very like the realistic perspective of the quantum kind of why one need to consider in the like the hardware like perspective. So because the idealistic situation correspond to the whole vibration, but that's actually indeed the idealistic. All right. So now let me just explain the curvature intuition. So this just takes just a short like the time to just explain. So let me just stop to record. Sorry, just stop to share the screen for a moment. So this is your way to think. Let me just compare three different like the situations. So now you know the reality of the computing the Gaussian curvature. So the real recipe. So let's just forget about the real recipe. So you know the intuition. So the intuition is what you need to explain. So can anyone explain the intuitive description of the Gaussian curvature? What is it? What was the intuitive description of it? I'm not talking about the recursive symbol whatsoever. I'm just talking the intuition. let me just repeat. So this is what you need to explain. You have a surface. In our case, we have a blue, either the blue sphere or weighted projective line. Is that okay with you? Sphere. So you choose the point that you'd like to compute the curvature. Okay? Choose the point. Then what you need to do is you need to consider all possible like the curves. So let me try to, I think it's also good to just draw for you. Plane, curvature intuition. Sphere. And let me draw one more thing. Cylinder. Like this. Okay. And I'm very like the bad at drawing the like the surface of the saddle point. So this is also a good example. You can just take a look. So surface of saddle point is kind of the like the potato chip. You know what I'm talking about. So surface of saddle point. So choose the point. Choose the point. Something like this. Then consider all possible like the curve passing through this point. So it's kind of like this, like this, like this, like this, like this, and so on. Here, like this, like this, like this, but there's no straight line. Here, like this, like this. Is that okay with you? So there are infinite many like curves on a chosen surface passing through the chosen point. Is that okay with you? Then the concept of the curvature, remember, concept of curvature was second derivative. Curvature means we want to distinguish either this one or this one or this one. In the curved level, this can be distinguished by looking at the second derivative. Are you with me what I'm talking about? The second derivative here is just a zero. Second derivative here is now positive, here being negative because the slope is changing. So the first case, you can see the slope corresponds to f prime. Okay, slope corresponds to f prime. Slope is increasing, meaning the f double prime should be positive on the like the target point. So in this case, slope is just a constant. So that's why f double prime should be zero. Slope is now decreasing. So that's why f double prime is now negative. So curvature corresponds to the second derivative. That's the most like important intuition regarding the curvature. Then now you have a bunch of the curves. Then you choose max curvature, and mean curvature. So that there are infinite many curves. Then for each of the like the curves, you just compute the curvature. Then it's possible to extract the max value and the mean value. Is that okay with you? Then you multiply. That's the concept of Gaussian curvature. Of course, now you know the reality, how complicated to really compute. But it does not really match or like in the first place, though I did those are exactly the same, but there's a way to prove it. It's okay, it just takes time. So so that first case, the plane, it contains the straight line, and actually it governs everything. Because of the straight line, what is the derivative? That's the second derivative, it's zero. So that's why the Gaussian curvature is just a zero everywhere for the plane. And as I already explained, for the cylinder, so cylinder, even though this part of the curve, it seems the curvature is non-zero, but it also contains a straight line. So if you multiply these two, then because we multiply by zero, so Gaussian curvature is still zero. Is that okay with you? Gaussian curvature is still just a zero. And as I already explained before, if the curvature values are the same, in fact, those two are the same surfaces. So you can see if we start from the Gaussian curvature zero plane, you can change smoothly to make the same surface. That's a cylinder. And because they are actually the same surface, it doesn't change the Gaussian curvature values. They are one-to-one correspondence. Does that kind of make sense to you? So that if the Gaussian curvature values are different, then they are different like the surfaces. But so you can see that if the Gaussian curvatures are the same, actually it turns out to be actually those two can be the same actual surfaces. Does that make sense to you? And the sphere case, because the or like the curved has the same phenomena. So if you multiply the max and the mean values, they have the same curvature sign. So the curvature, Gaussian curvature is positive everywhere, positive constant everywhere. That's the sphere. And like the surface of the saddle point. So if you just look at the sphere case, it's like this. And the saddle point look like something opposite, like this. So the Gaussian curvature is negative. So if the Gaussian curvature is that's a positive, so it should like this. So it's a kind of the umbrella. But if the Gaussian curvature is negative, then the behavior of the two curves should be different. So it's like something like this, like the center point, like the surface. In that case, the curvature is now negative. Then let me just finish to record just by saying just one thing for you to just think about it. So for the sphere, what is the sphere? CP1. What is the Gaussian curvature? Positive constant. This is coming from what? Collection of the gray circles or the orbits. Is that okay with you? So the orbits, if you just collect them, it becomes two-dimensional sphere. But if you now choose the weight differently, say A equals B, 2, B equals 1, then the gray circle is kind of the crazy like the orbit and collect them. Now the curvature does not behave in the same way. So as you already saw, curvature can be from negative infinity to positive infinity. Now it's kind of crazy, but that's more realistic. So let me stop to record here.